All right, so the spring force is a conservative force, which means that it's going to be very beneficial if we can determine a potential energy function that relates to this idea of K and delta X. Remember that a conservative force is one where when you use the force, or the force is acting as the object moves from A to B, and then it's also acting when it comes from B back to A along any path that the amount of energy is sort of back to the original amount. Energy is conserved, nothing is lost along the way. And that's true for an ideal spring, which is what we will focus on. So with that in mind, we do make a few assumptions that our springs are massless, meaning low mass compared to anything that's attached to them, and that the springs are ideal, meaning that they apply, or they obey Hooke's law, that negative K delta X. Sometimes that's called a linear spring as well. So we're going to have to first start with work, derive a function for the work being done by a spring, but then we'll quickly change to potential energy because it's much more useful. So the situation we're going to look at is a mass on a spring. You can picture this being horizontal or vertical, it really doesn't matter, but imagine that I have a mass here that is on a spring, and we're going to consider this to be our equilibrium point, so that's where X is 0. Now look at it at another moment that for whatever reason my mass is moving. Either we pushed it or something pushed it, whatever happens to be. And so at some moment it is at this position here, which I'm just going to call X sub I for initial. And then at some later moment I look and my box, my mass on my spring is all the way over here at X sub F. Again, I don't really want to worry about how that happened. Just that's the situation we're going to look at. And let's think about the force that the spring is exerting while this is happening. So if the object is moving to the right, then delta X is to the right. And that means that according to Hooke's law up here, my force of the spring is pointing the opposite way to the left. So they are opposite of each other. That's going to be important as we go to the next step. All right, so if I'm calculating the work being done by that spring force, work is the integral of F dr, or in this case we'll use dx since we're working along the x-axis, and we are moving, or the object is moving from some point we've called X sub I to X sub F. All right, so that's what we're going to be integrating here. So recall again the direction here. The force is pointing opposite to the displacement. And so there's going to be a negative sign that comes through there. That's what this negative refers to. And so we'll put in negative K, and we'll just call it X in this case because I'm not looking for the force as it moves through a distance. I'm looking at the force at a particular moment. So that's what I'm going to integrate from X sub I to X sub F. And we're going to do that with X as our variable, so we'll use dx there. Then of course when I integrate, I raise my exponent to x squared and divide by 2. And then I'm going to plug in my two endpoints, my boundaries of my integration. And so we get negative k x sub f squared over 2, and then minus a positive. I'm going to leave it as a minus here for later purposes. Sorry. So xk times x sub I squared over 2. All right, so we're taking the opposite of my difference between them. And that's really ugly looking, okay? But the nice thing about it is that if I look at potential energy instead of the work being done by the spring, a lot of these negative signs disappear. Let's take a look. All right, so here's the work relationship that we just derived, but recall from our discussions of energy that a potential energy function can be defined in terms of work. So the change in potential energy will equal the opposite of the work, which is just everything we just did, but drop that first negative sign. All right, so that's a little bit easier to deal with, a a few fewer negative signs. But we can do even one more thing. Recall with potential energy, if we all agree on a consistent 0 point, like a lot of times we use the ground when we're working with gravitational potential energy, if we pick a 0 point that makes sense, then we can make this even simpler. So what we're going to do is we're going to define that U is going to equal 0 when X is equal to 0, meaning that we're at the equilibrium point. And that way, if we just always work from that point, then this becomes a whole lot simpler. We can just change this whole thing into just saying that U, as a function of position, is K, that constant, not kinetic energy, the spring constant, times X, where X is how far the spring has been stretched or compressed from equilibrium, square that, and divide by 2. And so that is the way we'll work with potential energy for a spring. So when we add this into everything we've talked about before, we have learned before that, of course, work is the change in energy for a whole system. Now, I'm not going to include in this case the work due to gravity or the work due to a spring, because instead I'm going to use potential energy for that. But if I do have some sort of non-conservative force like friction or air resistance or something like that, then I can say this general statement. And the general idea is that the kinetic energy that I start with plus the potential energy that I start with, and then if I combine that with any work that's being done by those non-conservative forces like friction, that should tell me the kinetic energy that I end with plus the potential energy that I end with. And so this allows us to really handle just about any situation. My kinetic energy, it could be just 1/2 mv squared, but it also could involve something rotational. And so I just got to consider what type of motion I've got. My potential energy, it could be mgy, and both, either. It could be this idea of, wrong thing here. Or this could be this idea of kx squared over 2, where x is that stretch distance. Okay, so now we can handle a whole mess of other situations involving energy. And again, in many situations, energy is completely conserved, and so this is going to be able to be dropped, and we're just using the conservative values on both sides.